So hello everyone. So I'll talk about mainly about thermal transport in MOFs and some machine learning and high-throughput screening. So MOFs are rapidly growing classes of crystalline materials that are constructed from metal nodes and organic ligands. So there are over 90,000 synthesized MOFs and 500,000 predicted MOFs are known to date. So the MOF design space is really huge. Because they have open pores and large surface areas, they are attractive in many gas adsorption applications such as hydrogen storage, natural gas storage, and carbon capture. But the problem is they have low thermal conductivities because of their porosity and the complex chemistry, which inhibits an efficient transport of phonons. So that's problematic in many gas adsorption applications. For example, upon gas adsorption, we know that adsorption is an exothermic process. So upon gas adsorption, a significant amount of heat is generated. So if you don't dissipate that heat quickly enough, the temperature may raise, and at high temperatures, the gases starts to dissolve. And there's also like stability problem. Then not many MOFs are thermally stable. So by solving this low thermal conductivity problem, we can also help solve stability problem too. So there is a need to design MOFs with improved thermal transport properties. In the past, people have neglected this important property. Therefore, we don't know much about thermal transport. And although the MOF design space is really huge, we still don't know how to design MOFs with high thermal conductivities. So in my research, I use MD simulation and machine learning to study thermal transport in MOFs. So I'd like to briefly talk about the methodology we use to calculate the thermal conductivities. So there are like two branches of MD simulation to calculate the heat transport. So the first one is non-equilibrium MD simulation. So the concept is very simple. You just apply two thermostatic regions at both ends of simulation box. Then you calculate the temperature gradient, and you can apply this equation to calculate the thermal conductivity. The second one is equilibrium MD simulation. So it is based on Green-Kuber relation. So Green-Kuber relation states that the thermal conductivity is linearly dependent on time-dependent fluctuations in the flux. So this quantity called heat current autocorrelation function. So which means that if there is a strong correlation between heat fluxes at different time steps, then which means that the thermal conductivity is high. So we focus on equilibrium MD simulation in my research. Okay, so before we move to talking about some structure property relationships, I would like to talk about the Python package that was developed in our lab by Paul Boone. So it is a general purpose open source Python package for molecular find and replace. So in the context of molecular simulation, it is very useful operations, especially for adding swapping functional groups, adding defects, and especially for parameterizing structures with flexible force fields. We know that generating LAMMPS data files with all flexible force fields are not easy. So, and it's also very efficient. You can see that, this chart, the time it takes to do this find and replace operations for metal organic framework UIS 66. So it is originally developed for MOFs, but it can be used for any molecules or periodic crystals. So then we applied this for studying UIS 66. So this is the unit cell for the UIS 66. If you don't know about MOFs and UIS 66, it has FCA topology and the highest possible coordination, which makes this MOF one of the most stable MOFs. Then I would like to provide a couple of examples where the MOFan can be very useful. For example, this is the UIS 66 structure, and this is the search pattern, which is just the business decarboxylate linker. And if you'd like to replace this linker with functionalized version, and then you can use MOFan, and this is how the functionalized version looks like. Or the other example is if you'd like to introduce defects or just removing something from the structure, you can also use MOFan. It has very easy Python interface. You just need to load the structure, you need to load the search pattern and the replace pattern. You just call this function. And it reads many commonly used input the file formats. And so it has also, you can also use it using a command line interface. So this is an example for introducing defects. Another useful feature is you can replicate the structure for whatever number of dimensions you want. And you can also specify the defect fraction that you want to remove. So this is very useful, and we apply it, use it MOFan software to generate various defective UIS structures. And we wanted to study the influence of defects on the thermal conductivity. So this is how this missing linker and the missing cluster defects look like. So in the missing cluster defects, the metal node with all 12 connected linkers are missing from the unit cell. Okay, so we can use MOFan to randomly generate defects. We did that, but we are more interested in correlated defects. Correlated defects means not random, but symmetrically distributed defects, defects with some pattern. So like 10 years ago, like Andrew Goodwin from the University of Oxford, they experimentally showed that missing cluster defects form correlated defect nanoregions, which are shown here. It has own like a crystalline structure. Then later, like a couple of years ago, that was supported by another group. Importantly, they reported two other different types of correlated defects, which I'm going to show here. So the first one is, so this is the pristine UIS 66 without defects. So in the first step of missing linker correlated defects, the 8 face-on linkers are missing from the unit cell. So in the first step of missing cluster correlated defects, the metal node with all 12 connected linkers are missing from the unit cell. And the second type of missing cluster correlated defects, not only the metal node with all 12 connected linkers, but also the surrounding 4 but not connected linkers are missing the 2. So the difference between these two types of missing cluster defects, so it is more deficient in linkers. So we generated these structures using MOFan. Otherwise, it would have been very difficult to do it manually. And we had to do some tricks with MOFan, because MOFan randomly selects linkers and randomly deletes them. Okay, then we went and calculated thermal conductivities for that 3 defective structures with correlated defects. So the first one is just the FCU, like pristine UIS 66. Here I also showed a number of parallel and number of perpendicular linkers in each direction, because they are important to understand some of the results here. And so it's isotropic because the number of heat transfer pathways are equivalent in all directions. So in BCU, missing linker correlated defect, something interesting happened. So in Y direction, you see there's an improvement in thermal conductivity, but there's a decrease in thermal conductivity in other 2 directions. But overall, it had higher thermal conductivity than pristine case. So it's interesting how defects, improve thermal conductivity. So we have our own hypothesis. It seems that these 8 removed linkers, they were perpendicular to Y direction. So they acted as phonon scattering sources, so removing them improved the thermal conductivity in Y direction. However, they were parallel in X and Z direction, so they acted as heat transfer pathways. Removing them, therefore, decreased the thermal conductivity in the respective directions. So in real topology, it again, isotropic thermal conductivity, and similar thing happened in SU topology, where the thermal conductivity in Y direction a little bit improved, because these 4 removed linkers were perpendicular to Y direction. So this was like kind of pure serendipitous finding if you conclude this part with this animation. So if you, in this vertical heat transfer pathways, all these horizontal interactions act as phonon scattering, so they decrease the thermal conductivity. So removing them should increase the thermal conductivity in the vertical direction. So I think this is an important result, and it helps It shows that with careful tuning, we can improve the thermal conductivity in metal organic frameworks. Okay, so now I would like to move to the second part of my talk, which is about high-throughput screening and machine learning. So when people report structure property relationships by only considering small number of materials, oftentimes the reported structure property relationships might turn out to be different when you include many data points. And in the past, there are some great works on thermal transport properties of MOFs, but they focus on a small number of MOFs. So it is difficult to know whether their conclusions generalize well across all MOFs. So on the other hand, a data-driven approach where the large number of points are sampled from this vast MOF design space, it might support previously hinted structure property relationships, or it might also reveal the new ones that was hidden when small number of materials are included. So we have taken this approach and screened more than 10,000 hypothetical MOFs for thermal conductivity. So this is the largest screening work for MOF thermal conductivity. And these hypothetical MOFs was obtained using crystal generation algorithm called tobacco. So tobacco is topological based crystal constructor. It's a Python code or Python package, and so it is based on like top-down, so-called like reverse topological approach, where you have to first give the topological blueprint, then you will map the building blocks onto it. So this gives us, enables like to access every point in MOF design space, because it can also work with like edge-transitive or so-called like non-edge-transitive topologies, meaning that you can isotropically or anisotropically rescale the topological blueprint depending on the size of the building blocks. So we then, so it was developed by Yamil Collin and Diego Gomez-Galderon. It's a really good package. So then we selected kind of more than 1,000 topologies, and we think that the topology is very important to heat transport because they primarily dictate how the metal nodes and organic linkers are connected in three-dimensional space. And we included 40 different types of organic linkers. Many of them are aromatic, and 14 different types of organic nodes, and 24 different types of metal nodes. And we consider all possible types of coordination. And when you map this important, these building blocks onto this topologies combinatorically, that's how you will obtain this hypothetical MOF structures. And I didn't have space to include all 10,000 MOFs here, but here some of them. And as you can see here, they are diverse in terms of pore size, pore shape, in terms of building blocks, in terms of like the building blocks of chemistry of building blocks. So yeah, so hypothetical means that the experimental synthesizability is not guaranteed, and we think that's fine. We can still learn from hypothetical MOFs, and it's also possible that the MOF with the highest possible thermal conductivity was not discovered yet. So in which case, this is the way, I guess, to discover it. Or if you can't synthesize, let's say we find the very good hypothetical MOF. If you can't synthesize them, but we can synthesize a similar MOF structure to that hypothetical MOF. So it's, even if it's hypothetical, it's still useful. Then we went and calculated this important structural and compositional properties for that 10,000 MOFs. And because at the end of the day, these properties dictate the performance of MOFs in many practical applications. So as you can see here, for many of them, the range, this spans 2 orders of magnitude. Here I showed it like the minimum and the maximum calculated values. And we include like all possible types of coordination. Okay, now let's finally talk about the thermal conductivity values. So 97% of all MOFs had thermal conductivity less than 1, which is expected because MOFs have low thermal conductivity. But we were able to find 6 MOFs, including the 2 that had ultra high thermal conductivity. So like we were very lucky. We were able to find kind of needle in the haystack. And it's interesting to know how these 6 MOFs, including the 2, are different from the rest of 10,000 MOFs. And this important thing to mention is this thermal conductivity is the average of directional X, Y, and Z thermal conductivities, which we'll talk about. I'll talk about the directional thermal conductivity separately in later section. And so there are like so many interesting structure property relationships. So we published the results in a paper in Nature Computational Materials a couple of months ago. But here, like I would like to show like a couple of them. So this thermal conductivity versus 1 over density colored was void fraction. So high thermal conductivity favors high densities, intermediate values of void fraction. The same plot but colored with pore sizes, largest pore diameter. So high thermal conductivity favors small pores. And I remember like some people reported linear relationship between thermal conductivity and density by only studying a couple of MOFs. So here we see that the relationship is not linear and it's complicated. So, like high thermal conductivity is very important, but there are like some applications of MOFs that require low thermal conductivity, like thermoelectric energy conversion. So we found that some MOFs have ultra low thermal conductivity. And here I show the average pore sizes for that respective number of MOFs that belongs, that falls to this thermal conductivity range, and show also the average void fractions. They have this ultra low thermal conductivity is mainly contributed by ultra high pore sizes and voids. And but experimentally it is very difficult to synthesize MOFs with such a high pore sizes, after the solvent is removed. But still, it's interesting structure property relationship. So now let's focus on high thermal conductivity, which is more relevant and more important. It's again, we found like some couple of MOFs with some high thermal conductivities, and I also show the average pore sizes, densities, and void fractions. They all have small pores, high densities, but we cannot tell the difference for this ultra high thermal conductivity MOFs by just looking at this pore sizes and the densities and void fractions. They are very similar. So it turned out that there must be something else different for this 6 MOF, right? So we found that the 6 MOF, including the 2, have 4 connected square planar metal nodes. Interestingly, the diamond, the best known heat conductor material, and the recently found cubic boron arsenide, another best known heat conductor material, they both have 4 connected atoms. So we believe that these 4 connections are very special for high thermal conductivity, and there are no any paper that studied this 4 connected topology for in impact of 4 connection to heat transport. So we don't know why 4 connected leading showing high thermal conductivity, but we have our own hypothesis, which I'll talk in a moment. So this is the structural and the compositional properties for that 6 MOF with ultra high thermal conductivity. So this is how these 4 connected square planar metal nodes look like. And because of the time limit, I would like to show one of the 2 structure for one of the 2 ultra high thermal conductivity MOF. So here's the structure. The second structure is just a rotated version of this one. So it will be easier to understand it. So it has overall thermal conductivity higher than 30, and in X direction, the thermal conductivity is mainly contributed by strongly bonded covalent interactions that are highly aligned and parallel to X direction. And similar in Z direction, it's mainly contributed by covalent interactions that are parallel to Z direction. But in Y direction, we observed lower thermal conductivity, and it turned out that in Y direction, there is an additional perpendicular interactions across the plane. So remember our discussion with parallel and the perpendicular interactions. It's exactly similar thing happening here. In Y direction, there is an additional perpendicular interaction, which is causing this lower thermal conductivity. So it turned out that for connected square planar metal node allows this configuration. It provides parallel interactions in each dimension. Also, you can also minimize the perpendicular interactions in each direction. So what's happening here is that the thermal conductivity is maximized in X and Z direction, but it is minimized in Y direction. So we sacrificed Y direction because of the perpendicular interactions. So overall, we believe that the topology is very important for heat transport. And so the high thermal conductivity in MOFs is the right combination of right topology with right structural and composition properties. For example, if you just take this topology but use longer linkers, then you'll have higher pore sizes, then you won't get high thermal conductivity. Okay, so far we discussed about high-throughput screening of hypothetical MOFs, but with this MOF, 10,000 MOFs, we just cover only a small fraction of that huge MOF design space, and there are remaining 90,000 synthesized MOFs which we haven't touched yet. There are remaining 490,000 hypothetical MOFs. There are future MOFs which will emerge in the future. So we can't, and we still haven't discovered experimentally synthesizable and potentially high thermal conductivity MOF, because we cannot screen all of these possible MOFs with thermal conductive simulation because it's very expensive, and it took so many computing hours to screen all these 10,000 MOFs. So we need a faster technique. So we started using graph neural networks because we have 10,000 training data, and there are not experimentally measured thermal conductivities for MOFs. There are only a couple of them, and they are mostly on powder samples, which doesn't tell us about intrinsic thermal conductivity. So this is the only resource to train machine learning model for MOF thermal conductivity. So, and we also tried trained some other like traditional machine learning models with like MOF structure properties like pore sizes, densities. It didn't perform well. So then we went, then decided to use graph neural networks because graphs are a kind of natural choice for any molecules and structures, and we can represent nodes as atoms and bonding between them as edges. And there are like so many graph neural networks that have emerged over the last 5 years, and there are more coming. And some of them are very old, some of them are kind of recent. And I don't want to like talk details about the architecture of each one. I guess many of them will know us already about it. But the main core differences are in their like convolution operator. And so like, if you compare the convolution operator, for example, in GCN, they don't have edge features. They only do linear update on the nodes. Then in SGNet, I guess it's originally used for predicting atom-wise energies and forces for ML potential. And they started introducing this like radial basis function expansion to have continuous and a non-sparse representation for atom edges. For edge features. Then I guess the only difference in Magnet is they also do edge updates, and this other three models doesn't have edge updates. So Magnet is more kind of state-of-the-art GNNs for structure for property prediction of crystals. And then we trained all these 4 models, and we are training some other couple of new models. And then we did these hyperparameter optimizations, and for each model we did like 100 trials, and there's like a framework called MatDeepLearn. It's one of the best I guess framework for training many GNN models, and it also uses RayTune software to have this distributed hyperparameter optimization. Then we selected the best model that performed well on the validation data set. So now I would like to show like quickly the parity plot for each model separately, one by one. And so importantly here, we just focus on from 0 to 1 range, because that's where like 97% of all thermal conductivity data lies. And so it's not doing great, but not bad. And SGNet is a little bit better than GCN. And this is the result for CGCNN. It's better than SGNet, and this is Magnet. So Magnet outperformed all other 3 graph neural network model. So the problem is here. We are training on the average thermal conductivity, the average of Kx, Ky, and Kz. So there's an information loss, right? You can have these 2 different structures, like have different directional thermal conductivity, but if you average them, you'll have the same thermal conductivity. So there's an information loss, but you are still forcing these GNN models to learn, features. So that's problematic, and then we need to design a model that can predict directional tensor components of this thermal conductivity tensor. Then we changed the code for CGCNN so that it can output 3 thermal conductivities instead of just 1. Then, so interestingly, the result is a little bit better than Magnet. So, in predicting the average thermal conductivity. So we're changing the code for other 3 models, and we are training trying to develop model that can predict, this directional thermal conductivity features. So another problem that we are facing is the distribution of our data. So it's concentrated on lower end. But we have to develop a model that can predict all spectrum of thermal conductivity values, right? So how do we do that? We need to have more structures with potential high thermal conductivities. So then we tried to do some active learning. Then we generated, after training these GNN models, we generated another 2 million hypothetical MOFs using tobacco and predicted their thermal conductivities using GNN model. Then we selected top 500 MOFs and performed MD simulation to get their ground truth. Then we kind of put it back to our original data set. So we just did 1 cycle so far, and we are doing more. But here you can see the distribution of that, the distribution of thermal conductivity values using, calculated using MD simulation for that 500 MOFs. And here you can see we have some high thermal conductivity MOFs. So it is the GNN model, although not doing great, but it's still helping us to discover new hypothetical MOFs with potentially high thermal conductivity. And interestingly, if you look at the topology for that 500 MOFs, 80% of them have this CDZ topology. The topology of one of the two ultra high thermal conductivity MOF. So it's interesting. It's learning the topological blueprint of that MOFs. And so yeah, we are trying with this project is still ongoing project. And yeah, with that, I'd like to thank my advisor, Chris Wilmer, and our collaborators and our funding agencies, especially Peter Research for Center Computing and NSF. And thanks for your attention. I'll take questions.
Thank you, Meiirbek, for staying perfectly in time. Are there any questions?
Hi, thanks. Very interesting and comprehensive presentation, so thanks for that. I was curious, I think you were touching on it when you, on the last slide, come back to active learning. So of the MOFs that are selected from the neural network approach, almost like on a static topology, my immediate reaction was, once you perform MD simulation, are they stable? Do you get some subset of those that just collapse, so they're not viable even computationally? But I think once you do the full cycle, you'll screen out for that. But just curious about. Yeah,
not many of them are stable. That's why, we selected actually we selected 2,000 of them, but 1,500 of them failed because of that problem. But 500 of them runs fine because we also do before running thermal conductivity calculation, we optimize the structure. It's where it fails.
Yeah, absolutely. Okay, but I think this is addressing that, right? So
yeah. We only select the ones that that doesn't fail.
Yeah. No, that's
and the problem is with tobacco is it doesn't when you use, let's see, building blocks that are longer or have functional groups, they might atoms might get closer to each other. So it doesn't consider, so it still generates that MOF structure. But when you run them in the simulation, it fails because the atoms are closer to each other.
Right. No, that's great. Thanks. And then the last one's kind of a broader question, and I'm not even sure if there's an answer. I understand you have to get thermal conductivity on the empty, let's say, non-absorbed MOFs. But how would thermal conductivity change once gases start being absorbed?
Yeah, that's a very interesting question. So our lab have done many studies on that. So we also have experimental support. So when the gas absorbs, the thermal conductivity decreases because there is so-called phonon gas scattering. The kind of gas affects the vibration of atoms.
Any further questions? Sure.
How much experimental validation do you have for, because if you're running a lot of simulations, that's a key problem we keep running into. I guess, do you have any sort of error bounds on the range of how? Well.
Yeah, that's a very good question. We don't have done any validation because it's impossible. First of all, it's difficult to synthesize single crystal MOF, and it's even harder to calculate the thermal conductivity. So we don't have any papers that calculated the thermal conductivities of single MOF crystals. Yeah. But we are using UFF form of generic force fields, and it might not be very accurate, but so that's why we decided to do 10,000 MOFs. So a little bit kind of cover that weakness.
Yeah. For simpler, for simpler ones, what I'm really thinking of is some sort of, any sort of metal alloys or what. How do I put that? would it be possible to get that for any sort of simpler structures? Granted, you wouldn't be doing single crystals. You'd be doing like a several micron cube or several tens or hundreds of micron cube, for example.
Like to validate the force field?
Yeah.
Yeah, it's possible, but like, you know, we don't know. We're not experimental group, but you know, if there's like experimental collaborators, we are willing to do that.
Thank you.
Any further questions? Oh, sure.
Hi, really interesting talk. So I might have just missed something, but in the 10,000 or so MOFs that you studied, were all of those just identified, or are some of those MOFs that have already been synthesized but just couldn't have their thermal conductivity easily studied?
Yeah, some of them are, I mean, there's of course, there's an overlap between like experimentally synthesized and hypothetical MOFs. So yeah, some of them are already experimentally synthesized, and some of them, for some of them already there's some thermal conductivity values measured. But there, you know, I guess the highest measured thermal conductivity for any MOF is less than 1. Still, you know, we don't have high thermal conductivity MOF yet.
I maybe have a small question around tooling. So you mentioned this MOFUN tool.
Yeah.
I understand it's for creating a LUMS input file from a structure.
Yes.
Have you heard of the LUMS interface code?
Yeah. But it's a Baron Smith from Baron Smith group.
Mm-hmm. I used to be in Baron Smith's group, so I'm actually asking because I know that the maintainer of LUMS interface, I think, is no longer working on it. So if any of you guys are interested in taking some of the ideas from that code or kind of pointing people to yours, I think that might be interesting. Yeah.
I think some of our members in our lab, they found some like mistakes in the code. And they tried to fix it. I don't know what happened, but there are like, you know, when you assign like force field terms for many body potentials, there are like some like wrong force field terms were assigned. Yeah, so like the original purpose of this code wasn't only like parameterizing. It is developed for, especially for like functionalizing linkers and for introducing defects. Otherwise, we can't do that manually using molecular editors.
That makes sense. Yeah, just saying that it's an opportunity to maybe move a user base from one code to another, from one code that is no longer maintained to one code that is. So just putting that out there. Any further questions?
There's one.
I'm kind of curious, when you were introducing the defects into the structure, you were doing something with a file format I hadn't seen. I think like a CPK file format or CDK or something.
Yeah, CML?
CML, yeah. And it's interesting because I can imagine with metals you wouldn't want to use like common cheminformatics stuff because metals are weird and sometimes they don't fit well. But the defects that you were introducing look like they were in like a fully organic molecule. Would you consider using, I mean, for us, like our DKit is a really mainstream cheminformatics toolkit that would be able to do that defect stuff really easily if you have the chemical structure of the like organic scaffold. Is there a reason that you're using this instead, or is this based on geometry versus a molecular topology? I guess I'm interested in more information about this.
Yeah, so I haven't used RDKit before, so I don't know how it works. But yeah, we are using the CML is like, you know, you have to create this structure, a search pattern and replace pattern from scratch, right? So that's why we use Avogadro, and this CML works like, it's kind of natural file format for Avogadro.
Is it based on like a Kekulé structure of a molecule, or is it based on like a geometry of oh, it's based on a geometry. Okay. Okay, that's really interesting.
So I don't get your question. What do you mean by like geometry or like molecular? Like this algorithm, how it works?
Yeah, we'll go ahead.
So I think in order for MOFs, you really need to think about the structure of where you place things in space, right? So like you first have the topology, right, and then you connect. You need to have repeating unit cells of basically crystal unit cells. Can you do that with RDKit?
Yeah, sorry if this is all about me. It's kind of an interesting different paradigm because this is very much a molecule that's defined by elements and their positions relative to each other in 3D space. And I think in organic chemistry land, it's more common to have molecules defined as like a graph. Like that you can even have a molecule with no coordinates, but you just know its connectivity and its topology.
Right.
Yeah, and it's interesting because it looks like, it just struck me that you have a very organic looking molecule, but you're treating it as like a very like 3D molecule. Maybe it's just, this is my first time like dipping my toes into the field of MOFs, so it's cool to see how you're doing the modeling for them.
Yeah, we can talk more about it. Yeah. In person.
Well then, thanks. Let's thank Meiirbek again.
Thank you.